Welcome back. Problem 7-46. So statement is the beam is subjected to shear of 800 Newton. Determine the average shear stress developed in the nail alongside A and B. If nail are spaced 100 millimeter apart, each nail has a diameter of 2 millimeter. So you can see this is the beam, and that is made up of these wood that are nailed together at side A as well as at side B. These nails are spaced of 100 millimeter and having diameter of 2 millimeter, and a shear of 800 Newton is applied. So you have to find the average shear stress developed in this nail. So let's start with the solution. We know that shear flow is equal to horizontal shear force per unit length, which is the space, and that shear flow is also equal to V into Q divided by I. So what we do is that we have this V, we do not have Q, we do not have I. So we'll find first I, which is section property. So for section property I, which is not known, so we will first find the neutral axis passes through centroid. So because this beam is not symmetrical about a horizontal axis, so we'll first find the centroidal axis passing centroidal axis. So for that we have formula, which is y bar is equal to sum of y dash into a divided by sum of area. So let this is 1 and this is 2. Since a board and b are same, so we will write it y dash 1 y1 dash into a1 plus 2 times y2 dash into a2 divided by a1 plus 2 times a2. Now what is y1 dash? So if we take this upper surface as a reference line, so this is 1, so this area will be a1. So y dash will be equal to a1 is, you can see, 250 millimeter multiplied by 30 millimeter. Clear? So 250 millimeter in term of meter is 0.250 multiplied by its thickness, which is 30 millimeter, and 30 millimeter is 0.03. What is y dash? So y1 dash, so y1 dash is distance from the top surface till the mid of this first. This distance is y1 dash, and this y1 dash is 30 divided by 2, which is equal to 15 millimeter. So 15 millimeter is 0.015 plus 2 times a2. Now a2 is this area, which is 30 multiplied by 150 millimeter. So 115 is 0.150 multiplied by 30 is 0.03 into y2 dash. So y2 dash is distance from top surface till the mid of this second. This distance is y2 dash, and this y2 dash is 150 divided by 2, which is equal to 150 divided by 2, which is equal to 75 millimeter, and 75 is 0.075 meter, divide by area a1 area was 0.250 multiplied by 0.03 plus 2 times area 2, which is 0.150 multiplied by 0.03. So when you calculate it, you will get y dash, the location of neutral axis passing through centroid, is equal to 0.04773 meter, or you can say it is 47.73 millimeter. What does it mean? It means that from the top, the neutral axis or centroidal axis passing through its neutral axis, centroidal axis will be this one. So this distance from the top, this is your y dash, y bar, which is equal to 47.73 millimeter. Now you have I. So by using parallel axis theorem, we will find I, which is I is equal to sum of I dash plus AD square. So for first one, we will have 1 over 2, 1 over 12. I am talking about this one. So we'll first find the moment of inertia of this, which is equal to 1 over 12, its breadth, into h cube. H is 30 millimeter. So I will write 1 over 2, 0.250 in meter, into h is 0.03 whole cube, plus area. Area is again this 0.250 into 0.03 into d square. Now what is d square? So distance from neutral axis till the mid of this section. So this is your d1. This is your d1. So d1, you can see that it can be obtained if you subtract y1 dash from this. Clear? So y dash in meter is 0.04773 minus y1 dash is 0.015 whole square, plus 2 times 1 over 12. Now we will calculate the moment of inertia for this. So its breadth is 30 millimeter and height is 150 millimeter. So 1 over 12 breadth is 0.03 into height is 0.150 whole cube, plus area, which is equal to 0.03 into 0.150 into d square. Now what is d square? So d square is distance from neutral axis till the mid of second section. So this is the mid of second section and this is the neutral axis. So this distance is d2. So I will write this distance is d2, and this can be obtained if you subtract y dash from this y2. You can see that if you subtract this distance from this distance, clear? So you will left with this. So this distance y2 dash is again that was y2 dash was 0.075 minus y dash, which is 0.04773 whole square. So when you calculate it, you will get the moment of inertia for the beam shown above is 32.164 into 10 to the power minus 6 meter power 4. Now you have this I, you have V, you do not have Q. So what we will find Q? We know that Q is equal to y dash bar into A. So you can see that here this is the shaded portion. This one is the shaded portion in which we use this nail to connect with this. So this is the area A dash. So this is A dash, and y bar is distance from neutral axis till the mid of this section, which is this D1, and D1 was this one. D1, this value, this one. So I will write it 0.04773 minus 0.015 into area. Area is 250 millimeter, which is 0.250 multiplied by 0.03. So when you calculate it, you will get Q is equal to 0.245 into 10 to the power minus 3 cubic meter. Now you have V as well, so you can just put it in this formula. Q is equal to shear flow, which is horizontal shear force per unit length, is equal to V into Q divided by I. So V is equal to 800 pound. Q is 0.245 into 10 to the power minus 3 divided by I, which is equal to 32.164 into 10 to the power minus 6. So from here you will get the value of shear flow is 6105.4 Newton per meter. Okay. This 800 is not in pound, this is in Newton. So can you make this correction? So now we have shear flow. We know that shear flow is also equal to horizontal shear force per unit length. So you can just put the value of Q 6105.4 is equal to FH divided by S. S is the spacing, nail spacing, which is 100 millimeter. So 100 millimeter in term of meter is 0.1. So from here you will get horizontal shear force will be equal to 0.1 multiplied by 6105.4, and we will get horizontal shear force will be equal to 610.54 Newton. Now this I will write it, since each side of the beam resists this shear force, then average shearing stress in the nail will be equal to FH divided by 2 into area. You can see that you have nail on this side as well as on these sides, clear? So the shear force will be distributed divided by 2. So that's why FH divided by 2 into area. So FH is 610.54 divided by 2 multiplied by diameter of nail is given. So area is pi by 4 into 2 millimeter. In meter it is 0.002 whole square. So when you calculate, you will get the average shearing stress in the nail comes out to be 97.2 megapascal, which is the answer of this question. And that was all about this problem 7-46. I hope you have enjoyed this video. Those who are new to my channel, then I will request them to subscribe it, and don't forget to press the bell icon. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 6-83 that is taken from chapter number 6, bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the shaft is supported by smooth thrust bearing at A and smooth general bearing at C. If material has an allowable bending stress is 24 ksi, determine the required minimum diameter of shaft to the nearest 1/16 inch. So you can see this is the shaft that is having diameter D, clear, and at A we have a smooth thrust bearing, and at C we have a smooth general bearing. At B we have a load of 3600 pound, and at D we have a load of 1800 pound. So for the material, allowable bending stress is 24 ksi, so you have to determine the smallest diameter D to the nearest 1/16 inch. So let's start with the solution. So we know that allowable or maximum bending moment, bending stress is equal to maximum bending moment into C, which is the radius of this shaft, divided by I. So we know that for I, for this shaft having radius C, where C is equal to radius, diameter is given and C is radius, and this C is equal to D divided by 2. So for circular shaft having radius C, is I is equal to pi by 4 C power 4. So when you put it in this formula, so allowable bending stress is equal to maximum bending moment into C divided by pi by 4 C power 4. So from here you will get C3 will be equal to maximum bending moment, clear, maximum bending moment into 4 divided by pi into allowable bending stress, and this C will be equal to, radius will be equal to cubic root of maximum bending moment into 4 divided by pi into allowable bending stress. So once we will find C, so we can find the diameter. Now you can see here C will require the maximum bending moment, clear, and allowable is given. So we will find this maximum bending moment by using shear force and bending moment diagram. For that, first step is that if you remove this smooth thrust bearing at A, so you will be having a reaction force RA by the bearing on this shaft. Similarly, if you remove this smooth journal bearing at C, so you'll be having a reaction force RC by this bearing on this shaft. So we'll find this RA and RC by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point C is equal to 0 and taking the counterclockwise moment as positive. So about point C, first moment is this RA into perpendicular distance is 6. This is clockwise, so it will be negative. So I will write minus 6 times RA. The second moment will be this 3600 into perpendicular distance is 3, and this is counterclockwise, so it will be positive. So I will write 3600 into 3, and the last moment is due to this 1800 and perpendicular distance is 3, and this is clockwise, so it will be negative. So minus 1800 into 3 is equal to 0. So when you solve this, you will get 6 RA will be equal to 5400 and RA will be equal to 900 pounds. Now you have this RA, so you can find this RC by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is plus 900 because it is upward, minus 3600 plus RC, which is not known, minus 1800 will be equal to 0. So from here you will get RC will be equal to 4500 pounds. Now you have RA and RC, so you can find the shear force and bending moment diagram. You can draw it. So for that I will take the vertical line from the end of this beam and a horizontal line to show the length, which is in feet. X is in feet. We have V on y-axis having unit pound. Clear? So let each division is 500 pounds. So 500 are 1000. Similarly, minus 500. This will be minus 1500. This will be equal to minus 2500 pounds. This will be minus 1000, minus 2000, etc. Clear? Now we'll plot first point, and the first point is at point RA. We have RA which is 900, so your first point will be 900. So 900, let 900 is this point. Now moving from point A till point B, there is no other force, shear force, so it will be 900. But at point B we have load of minus 3600, so it will change to minus 2700 at point B. So shear force will change to minus 2700. So let 2700 is this one, minus 2700. So shear force will change from this to this. Now moving from point B to C, there is no other shear force, so it will remain horizontal. But at point C we have RC, which is 4500. So minus 2700 plus 4500 will give you 1800 plus value. So we'll locate 1800. So let 1800 will be somewhere here, because this will be 1500 and this will be 2000 pound. So shear force will change from minus 2700 to 1800. Clear? And moving from C to T, there is no other shear force, it will remain horizontal, and at the end you can see minus 1800 downward will cause it to 0. So this is your shear force diagram. Now we'll draw the bending moment diagram. So for that, again I have to draw a horizontal line to show X in feet, and on y-axis we have a bending moment that will be unit pound into feet. Let one division is 1500, so 1500, this will be 3000. Similarly, minus 1500, minus 3000, minus 4500, and minus 6000. Clear? And at X is equal to 0, we have movement will be equal to 0. Now first area under the shear force diagram is this area, and this area is equal to 900 multiplied by this length, which is 3 feet. So that will be equal to 2700. So first point at this we will have 2700. So let 2700 is this one. Now you can see shear force is a horizontal line with 0 degree. So bending, and this area is positive. So bending moment will be 1 degree higher. It will be a linear line, and slope will be increasing. So we'll join these 2 points. The second area is this area, and this area is equal to minus 2700 multiplied by 3 feet, and that will be equal to 8,000 minus 8,100. So plus 2700 minus 8,100 will be equal to minus 5,400 at this point. So we'll locate minus 4,500. For example, if this is the point, minus 5,400. Now you can see shear force is a horizontal line, and this area is negative, so bending moment will be a linear line and slope will be decreasing. So we'll join these 2 points using straight line. The third area is this area, and this area is equal to 1800 multiplied by this length is 3 feet, so that is equal to plus 1500. So minus 1500 plus 1500 will bring to 0 at this point. Clear? So this will be your next point. Now shear force is a horizontal line with 0 degrees, so bending moment will be 1 degree higher and slope will be increasing because area under the shear force is a positive area. So this is your bending moment diagram. Now from this BMD, clear, this BMD, we have maximum absolute value of bending moment is equal to minus 4500 pounds into feet. So this maximum bending moment is equal to 5400 pounds into feet, and we want to convert it into pound into inch. So 1 feet is equal to 12 inch. So I will multiply it with 12 and unit will be pounds into inch. That will be the maximum absolute value of bending moment. Now put it in this formula. So we will get C is equal to maximum bending moment, which is 5400 multiplied by 12 into this formula. We have 4 divided by pi into allowable bending stress is 24 ksi. So I will write 24 into 10 to the power 3. That will be psi, pound per square inch. And we will have a cubic under root. So when you solve this, clearly you will solve this. So you will get C, and that C will be equal to 1.51 inch. So we need diameter. So diameter is equal to 2 times radius. So 2 multiplied by 1.5, 1.51 will bring it to 3.02 inch. Now you have diameter is equal to 3.02 inch, clear, and we have been given to calculate the minimum diameter nearest to 1/16. So 3 inch is 3 plus 0.02 inch. So 1/16, we know that 1/16 is equal to 0.0625, which is greater than this value. So but we have been asked nearest to 1/16 inch. It's clear? So we will choose the diameter D is equal to 3 1/16 inch. And this is the answer of our this question. So 3 into 1/16 inch diameter is selected or calculated for this shaft under the given loading and for allowable bending stress of 24 ksi. And that was all about this problem 6-83. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 6-27. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is draw the shear and movement diagram for the beam. So you can see this is an overhanging beam and there is a triangular load of magnitude W0 at this end. At this end load is 0. There is a roller support at A, and at point B we have pin support. So you have to draw the shear and movement diagram for the beam. So let's start with the solution. So first step is that if you remove this roller support at point A, so you will be having reaction force offered by this support on this beam will be RA, and if you remove this pin support, so there will be a vertical reaction force of RB on this beam by this support. So first we will find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise movement as positive. So you can see one load is RA, the second is RB, and the third one is, if this triangular load is converted into a point load, so it will be equal to W1/2 into W0 into the length over which act, and this total length of the beam is equal to L. This is L because 2L/3 plus L/3 is equal to L, and that will act at a distance of L/3 from point B or from denser side. So this will be L/3. Now we apply this equation of equilibrium. So RA into perpendicular distance is 2L/3. Let me show you. This is RA, and about point B, this perpendicular distance is 2L/3, and this is producing clockwise, so it will be negative. So I will write minus the second moment that is produced due to this load and perpendicular distance is L/3 here, and this is producing counterclockwise movement, so it will be positive. Here I have L as well because it is acting over length. So plus 1/2 this load, which is 1/2 W0 into L, and perpendicular distance is L/3 is equal to 0. So from here we will get minus 2 RA L divided by 3 plus 1/6 W0 L square is equal to 0. So you will get 2 RA L/3 is equal to 1/6 W0 L square, and when you calculate, RA will be equal to W0 L/4. So this is the value of RA. Now we'll find this RB by using equation of equilibrium, that sum of all force along y direction must be equal to 0 and upward force is taken as positive. So RA and RB are upward, so RA is W0 L/4 minus this force, which is W1/2 W0 into L plus RB is equal to 0. So if you take LCM, so this will be 4. So it will be W naught L minus 2 W naught into L plus RB is equal to 0. So this will give you 4 minus W naught into L plus RB. So from here you will get this RB will be equal to W naught L over 4. Now you have RA and RB. So what we are going to do is that we will cut the beam at this and at this section. Let this is section AA and this is section BB, and we will find the equation of shear and moment as a function of x, clear, and then we will put the value of x to find the shear and moment and then draw the shear force and bending moment diagram. So first step is that if you cut this beam over here, clear, and this, let this distance is x, this is section 1 and draw the free body diagram. So let me draw it first. Let this is the beam, clear, and you will be having a triangular load, clear. This is the triangular load. This is the distance x where you cut this beam, and when you cut it, you will be having a shear force V and you will be having moment M. This is your point 1, clear. Now you can see that here the load is W naught. So if you take the ratio, we have two similar triangular, one is this one and the other one is this one. So this is for the length of L and this is for length of X, clear. So by using similar triangles, if I take the ratio, this W naught over length L, W naught over length L will be equal to, here let the magnitude is W, so W divided by this distance X, so W divided by X. So where we will find W will be equal to W naught into X divided by L. So here the magnitude will be W is equal to W naught into X by L. Now when you convert this triangular load into point load or concentrated load, so it will be equal to 1 over 2 this load, which is W naught X over L, and the length over which act, and that length is X, and that will be acting at a distance of X by 3 from this point 1. Now we'll find this V and moment by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. And remember that section AA is for x is greater or equal to 0 and less or equal to L by 3. So x start from here is equal to 0 and at here you can see x is L by 3. So this equation will be valid for this region, clear. Now V is downward, so minus V minus this load is downward. So minus 1 over 2 W naught X square over L is equal to 0. So from here you will get V is equal to minus W naught X square over 2L. Let this is your equation number 1. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about point 1, the one moment is due to this, which is this load into perpendicular distance is x by 3, and this is producing counterclockwise moment, so it will be positive. And this external moment which we have taken as this will be positive. Now you can see that this load is producing counterclockwise movement, so in order to balance it, it will be in this direction. So let me correct it. This direction is this. So this minus movement, which is clockwise, plus 1 over 2 into W naught X square over L into perpendicular distance is x by 3 is equal to 0. So from here you will get this movement will be equal to W naught X cube over 6L. Clear? And this will be your equation number 2. So this equation 1 and let me write it, equation 1 and 2 are valid for x is greater than or equal to 0 and less than L by 3. Now what we will do is that we will cut the beam at any region, that this is section 2 and this region is x is greater than or x is greater than L by 3 and less or equal to L. Clear? And we will draw the free body diagram. So let me draw it over here. So that this is the beam. Here there is a triangular load over here. Clear? This is the triangular load. At distance of L by 3 we have RA. So this is L by 3 and this is RA, and RA is W naught L over 4. And the total distance from this till the end of the beam is X, where we have cut this beam. So the remaining will be equal to X minus L by 3. And what about the magnitude over here? It will be the same, just like W naught X over L, because you can see you will have a two triangle, similar triangle. One is this one and the second one is this one. So W naught over L is equal to W over X, and this W will be equal to W naught X over L. Okay, W naught. So when you cut it, you will be having a shear force, clear, like this, and you will be having a moment that will be counterclockwise. Why? Because you can see now you have this force and this force as well. So we have taken it counterclockwise because its effect will give you a positive moment. Okay, so let this is your point 2 because it is section at point 2. So when you convert this triangular load into a point load, so it will be equal to 1 over 2 this load, which is W naught X over L, clear, and it will act at a distance of x by 3 because x is the total length. It will be x by 3. Now we'll find this by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. And remember that this is for section 2 and here x is greater than L by 3 and less or equal to L. Clear? So W naught L by 4 which is acting upward, clear, minus this load which is downward minus W naught X over L, clear. So this load here you can see 1 over 2, this load into the length over which that is X. So it will be W naught X square minus W naught X square over L, clear. And the last thing is that minus V is equal to 0. So from here this V will be equal to minus it will be equal to W naught L by 4 minus W naught X square over L. Or you can say this V is equal to minus W naught X square over 2L. Here you can see you have 2 as well, so it will be minus 2, clear. So minus W naught X square over 2L plus W naught L by 4. This is your equation number 3. Now you'll find movement by using equation of equilibrium, that sum of all movement about point T is equal to 0 and taking the counterclockwise movement as positive. So about point 2 first movement is due to this W naught L by 4 and perpendicular distance is x minus L by 3. This is producing clockwise movement, so it will be negative. So I will write minus W naught L by 4 into perpendicular distance is x minus L by 3. The second movement will be due to this load and perpendicular distance is x by 3 and it is producing counterclockwise, so it will be positive. So I will write this load which is plus 1 W naught X square over L into perpendicular distance is x by 3 and there is external movement which is positive. Their sum must be equal to 0. So when you solve this, you will get this movement will be equal to minus W naught L over 4 into x minus L by 3 plus W naught X cube over 3L. Okay, just wait a minute. This is W naught X square over W naught X square over 2L. So this will become equal to 6L. Okay, now it's okay. Then this is your, this will be positive, M will be equal to, this will be positive and this will become negative. Okay, so this is your equation number 4. Now we have equation 1, 2, 3, 4. This equation 3 and 4 are valid for x is greater than L by 3 and less or equal to L. Clear? Now we'll move to draw the shear force and bending moment diagram. For that I have to copy these equations. Let me copy these equations, some portions, so that we can move toward next page. I will copy it. I will move to second page and we'll paste here. Okay. So for shear force and bending moment diagram, I have to draw vertical lines from the end of this beam. You can see here, and there is a horizontal line to show the length in x, which is not known either in meter or in inches. So here we will draw the V. Now first, what we will do is that you have all these equations. So for x is equal to 0, put in equation number 1. Equation 1 is this one. So if you put x is equal to 0, so you will have V is equal to 0. Now for x is equal to L by 3, put in equation number 1. So what we will get if you put x replaced with L by 3, so you will get shear force will be equal to minus 1 over 8 W naught into L. You can put it and you will get this value. So this, kindly correct it. This is V is minus 1 over 18 W naught into L. We can put it V is equal to minus W naught. You will replace L by 3 whole square over 2L. So that will be minus W naught L square over 18L, which is equal to minus W naught L over 18. Clear? So I will again remove this. Now for x is equal to L. Clear? So put the value, put in equation number 3. So this is your equation number 3. So when you put x is equal to 3 in that, so what you will get is that you will get V is equal to minus W naught L over 4. Now you can see that at the end you will have RB, which is equal to W naught L over 4. It means that this will bring it to 0. So in between, let me plot it as well. So at x is equal to 0, we have first point is this one. At x is equal to L by 3, which is this one. Clear? So we have V is equal to minus 18. So let minus 18 W naught L minus W naught L over 18. Minus W naught L over 18 is this one. Clear? And you can see you have RA as well over here. So which is W naught L over 4. So minus W naught L over 18 plus W naught L over 4 will bring it to 7 W naught L over 36. Okay, so you can see that this the shear force, the loading is triangular, so the shear force will be second degree curve and it will be like this. So let me join first these 2 points like this, like a curve. At this point you have plus 40, which will cause it to 7. So let 7 W naught L over 36 is this point. So shear force will change from this till this point. This is the point. Okay. Now at the end we have minus 4 W naught L over 4, which let this is minus W naught L over 4, and at the end you have plus, which will cause it to come to 0. And you can see that this load is again a linear load, so shear force will be a second degree curve and it will be like this. It will be like this. So we'll join these 2 points by using curve, not a straight line, and trying it to draw like a curve. Okay. Now here you can see the shear force is equal to 0. Clear? And we will find the location where this shear force acts, because at this location the bending moment will be the maximum. So you will find this value of x, which is not known. So what we will do is that put v is equal to 0 in equation number 3. So it will be equal to 0 will be equal to minus W naught x square over 2L plus W naught L over 4. So what we will get from here, that x will be equal to let me check it. This will give you x square is equal to L square over 2, and x will be equal to 0.707 L. Clear? So this is x is equal to 0.707 L. So you can put this value of x in this equation number 3. So you will get v will be equal to 0. We will move toward bending moment diagram. So for bending moment diagram, I will again draw a horizontal line, and here x will be the length, and on y-axis we have moment. So what we will do is that for x is equal to 0, put in equation number 2. This is equation number 2. So if you put x is equal to 0, so moment will be equal to 0. So your first point will be this one. Here moment is 0. Okay. So for x is equal to L by 3, put in equation number 2. Equation number 2. So this is your equation number 2. You can see. So if you put x is equal to L by 3, so what we will get after the calculation, or after simplifying, you will get moment will be equal to 0.00617 W naught L square. I have already done it, but for reducing the length of the video, you can do it by yourself and you will get this value. Now you can see this is a positive value. Clear? This is a positive value. So while representing this positive value on moment diagram, it will cause the bending moment to go downward. So let this point is minus 0.00617 WL square. This is a convention given in the book. And you can see that this shear force is a second degree curve, and you can see the moment is 3 degree equation. So it will be just like, it will be also a third degree curve, and the bending moment will be like this, starting from 0 till this end. Okay. Now for x is equal to 0.707 L, put it in equation number 4. That will give you maximum bending moment. This is your equation number 4. So if you replace x with 0.707 L, so you will get the maximum moment, which will be equal to 0.0345 W naught L square. So we look at this point. Clear? And this will give you the point will be like. Welcome back. Problem 6-191. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Materials by R.C. Hibbeler. Statement is determine the shear and movement in the beam as a function of x, where x is greater than 0 and less than 6 feet. Draw the shear and movement diagram for the beam. So you can see this is a cantilever beam here, where there is a point load at this end, which is 8 kips. At a length of 4 feet, we have clockwise movement of 50 kips into feet, and there is a distributed load from fixed end till the length of 6 feet, and the magnitude is 2 kips per feet. So we have to determine the shear and movement equation in terms of x for the region x is greater than 0 and less than 6 feet, and then we will draw the shear force and bending moment diagram. So let's start with the solution. If we remove this fixed support at this end, so we will be having a reaction force. Let this is your point number 1. So there will be reaction force, which is R1, and there will be a moment as well. Clear? So this we will find this R1 and M1 by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about this point 1, one moment will be due to this 8 kips load, and the perpendicular distance is this 10 feet. And this is producing clockwise moment, so it will be negative. So I will write minus 8 into 10. The second moment is this one, which is 50 kips per feet into feet, and this is again clockwise, so it will be also negative. So minus 50. Now you can see you have a distributed load, so we will convert this distributed load into a point load. So for that, we will multiply this 2 kips per feet with the length over which it acts. So 2 into 6, which is 12, and this load is acting downward, and that will be acting at a half of the total length. The total length is 6 feet over which this distribution load acts, and the half will be 3 feet. Okay, so the third moment will be due to this 12 kips load, and perpendicular distance is 3, and this is also producing clockwise movement, so it will be negative. So I will write minus 12 into 3. And the last moment is this reaction moment, which is counterclockwise m1, and that will be positive. But the sum of all moment about point 1 must be equal to 0. So from here we will get m1 minus 80 minus 50 minus 36 is equal to 0, and we will get this m1 will be equal to 166 kips into feet. So this is the reaction moment when you remove this fixed support. Now we'll find this R1 by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward forces taken as positive. So R1 is upward, 12 is downward, that will be minus, and minus 8 will be, their sum must be equal to 0. So R1 minus 12 minus 8 is equal to 0. So it means that R1 is equal to 20 kips. Now you have R1 and moment M1. So what we will do is that we will section this beam in the range of x is greater than or equal to 0 and less than 6 feet and draw the free body diagram. So if I draw it over here, that this is the beam, this is point 1 where we have a reaction force R1. R1 is 20 kips, and the moment was, we calculated, is 166 kips into feet, that is counterclockwise. And this length which we have cut the beam is x, and there is a distributed load over a length of x, and this distributed load is downward. So when you convert this distributed load into point load, so it will be acting at the mid, clear, and the magnitude of this distributed load is 2 kips per feet. So this point load will be equal to 2 into x, and that will act at a half of the x. So this will be equal to x by 2, and the remaining will be also x by 2. And when you cut the beam, you will be having a shear force that will be, you will take it downward, V, and you will be having a reaction moment M. So we'll find this V and M in terms of x. How we'll find this? So by using equation of, let this is point O. So we'll find this M and V by using equation of equilibrium. The equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So 20 is upward, minus 2x is downward, and minus V, their sum must be equal to 0. So 20 minus 2x minus V is equal to 0. So from here we will get V is equal to 20 minus 2x, and the unit will be in kips. This is your shear force. Let this is equation number 1, which is the equation of shear in terms of x, and this is for region x is greater than or equal to 0 and less than 6 feet, where we have cut the beam. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0 and taking the counterclockwise moment as positive. So about this point O, the first moment will be due to this 2x, and perpendicular distance is x by 2, and this is producing clockwise moment, so it will be positive. So I will write 2x into perpendicular distance is x by 2. The second moment will be due to this 20 kips load, and perpendicular distance is x, and this is producing clockwise, so it will be negative. So I will write minus 20 into x. The third moment is this 166, that is clockwise, counterclockwise moment, so it will be plus. So I will write plus 166, and the last moment is external moment, which is considered as counterclockwise, so it will be also positive, and their sum must be equal to 0. So from here you will get m plus x square, because 2x into x by 2 will be x square, minus 20x plus 166 is equal to 0. So this moment equation will be equal to minus x square plus 20x and minus 116, and the unit will be kips into feet, and this is equation number 2. So equation number 1 and 2 are shear force and bending moment equations in term of x, and here you will use x is greater than 0 and less than 6 feet. Clear? So this is the answer of our first part. Now we'll move toward drawing the shear force and bending moment diagram. So for what we will do is that we will take the vertical line from the end of this beam, and first we will draw the shear force. So for shear force, I will take a horizontal line to show length x in feet, and on y-axis we have shear force, and unit will be kip. Clear? So what, let one division is equal to 5. So 5 plus 10 plus 15 and plus 20, and similarly downward, that is minus. Okay. So for region of, if I draw a table, clear, and the table will be like that, x value shear force in kips, and moment will be kip into feet. So for x is equal to 0, you can put it in this equation number 1. So when you put x is equal to 0, this v will be equal to 20. So I will write V will be equal to 20 kips. And for x is equal to 0, so this will be 0, this will be 0, and moment will be minus 166. So I will write minus 166. Similarly, for region of x is 6 feet. So if you put x is equal to 6 feet, so it will be minus 12. So 20 minus 12 will be equal to 8 plus 8. So V will be plus 8. Similarly, you put x is equal to 6 feet in this equation, and you will get moment will be equal to minus 82. Okay. So for x is equal to 0, we have V is equal to 20. So what we will do is that for x is equal to 0, our first point is this one. Clear? And for x is equal to 6 feet, so this is 6 feet length. We have shear force is 8 plus 8. So we will locate plus 8. So plus 8 will be somewhere here. Let me choose the point. This will be plus 8. Now you can see that shear, this loading is a uniformly distributed load, a load with a horizontal line of 0 degree. So shear force will be 1 degree higher as the load is downward. So it will be a linear, the shear force will be a linear line and slope will be decreasing. So we'll join these 2 points using straight line. So this will be the loading. Now in moving from this point till this point, we do not have any other force, so shear force will remain horizontal. So it will be remain horizontal till the end, and at the end you can see you have minus 8 downwards, so that will cause it toward downward 0. Clear? So this will be your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, I take a horizontal line to show the length x in feet, and on y-axis we will having moment that will be unit kips into feet. Let one division is of 100, so minus 100, minus 150, and minus 200. So for x is equal to 0, we have moment is equal to minus 166. So minus 166, let minus 166 is this point. This is minus 166. And for x is equal to 6, we have moment is minus 82. So let minus 82 is this point. Minus 82 is this point. Minus 82 kips into feet. Now you can see that shear force is a linear line with slope decreasing. So bending moment will be second degree curve, and it will be in clockwise. Rotation will be in clockwise direction. So we'll join these 2 points by using a curve. Okay. At this point, you can see you have external movement of 50 kips into feet, that is clockwise. So while drawing in bending moment diagram, it will cause the bending moment to go upward. This is convention given in the book. So minus 82 plus 50 will be equal to minus 32. So bending moment will change to minus 32. So let this point is minus 32. So your bending moment will change toward this. Okay. And the last one is this area under the shear force diagram, and you can see this area is, this height is 8 multiplied by length is 4. So 8 fours are 32. So minus 32 plus 32 will be equal to 0 at this point. So you will get the shear bending moment 0 at this point. And we will join these 2 points using a straight line here, and that will be your bending moment diagram. And which is the answer of our second part. So that was all about problem 6-191, in which first we solved the shear force and bending moment equation in terms of x, and then we draw the shear force diagram and bending moment diagram. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 1-77, that is taken from chapter number 1, stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the tension member is fastened together using 2 bolts, one on each side of the member as shown. Each bolt has a diameter of 0.3 inch. Determine the maximum load P that can be applied to the member if allowable shearing stress for bolt is 12 ksi and allowable normal stress is 20 ksi. So you can see this is member 1 and this is member 2 that are held together by using a joint having bolt on one on each this side and other one on the other side. And this is exerted by a tensile load P. So you have to find the maximum load or allowable load P that can be applied on this joint or on this tensile tension member. So let's start with the solution. So what will be the first step is that first step is if you cut this or if you separate this members and draw the free body diagram. So it will be like this. Let me draw it first. This will be member. You can see this is a load P, clear, and this angle is 60 degree. So when you separate it, so you will be having a normal force perpendicular to this surface, clear, and this will act, we take it upward, and there will be a shear force on this surface, clear. This will be a shear force. This is V, and this will be equal to normal force. So we'll find this normal force and V in this member, because you can see that this normal force, this shear force will tend to shear this bolt, and this normal force will cause the tension in this bolt. So based on these 2 criteria, we'll find the maximum load that can be applied on P. So we will find this equation, N and V by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and y direction is taken in this, because you can see you have N in this direction and V is in this direction. So what we are going to do is, if you draw a line parallel to this 60 degree, clear. So if you will draw a line parallel to this 60 degree, so this P will have 2 components. one along this axis, which is equal to one along this axis and other along this, parallel to this n. So this will let this is equal to x component and this is equal to y component. So you can see px will be equal to p cos of 30 degree, p cos of 60 degree. Clear? And this py will be equal to p sine of 60 degree. And you can see when you apply this equation, so you can see the force in this direction is n and other force in this direction is py, which is equal to p sine of 60. Their sum must be equal to 0. So I will write n minus py, which is p sine of 60 degree. Clear? Is equal to 0. So from here, this n will be equal to p sine of 60 degree. Clear? And this p will be equal to n divided by sine of 60 degree. So that will be equal to 1.1547 n times n. Clear? So I will write it, p will be equal to 1.547 times n. Let this is your equation number 1. Now we will apply another equation that sum of all component in x direction must be equal to 0 and force in this direction is taken as positive. So you can see v is in this direction and px is in opposite direction. So plus v minus px is equal to 0. So I will write v minus px is equal to 0. So we know that px is p cos of 60 degree. Clear? So from here that is equal to 0. So v is equal to p cos of 60 degree. Clear? And p will be equal to v divided by cos of 60 degree, and that will be equal to 2 times v. So I can write p is equal to 2v. That this is your equation number 2. Now you can see that here p is based on the normal force and here in 2 it is based on shear force. So what we are going to do is that we will first apply a criteria. We'll apply criteria based on allowable shearing stress. Allowable shearing stress. So we know that allowable shearing stress is equal to v divided by area, since there are two bolts, one on this side and other one is on another side. So we will take this v is equal to we do not know v, so clear, I will write v divided by 2 bolts, so 2 multiplied by pi by 4. Diameter of bolt is given as 0.3 inch, so I will write 0.3 square. And allowable shearing stress for bolt is 12 ksi, so I will write 12 into 10 to the power 3 is equal to v divided by 2 will cut with this, so we will get pi by 2 into 0.3 square. And from here we will get v is equal to 12 multiplied by 10 to the power 3 multiplied by pi by 2 into 0.3 square. And you will get the shear force comes out to be 1.696 kip. Now you have this v, so put it in equation number 2. Put in equation 2. So you will get p is equal to 2 times v, and that is equal to 2 multiplied by 1.696 kip. So you will get this p will be equal to 3.39 kip. Now this is the tensile load based on, it is based on shear stress, allowable shearing stress. Now what we will do is that we will use, this was the first criteria, we will use second criteria based on allowable normal stress, and we know that allowable normal stress is equal to normal force divided by area. Since there are two bolts, so I will write n divided by 2 multiplied by pi by 4. Diameter of bolt is given as 0.3, so 0.3 square, and allowable normal stress is given as 20 ksi. So 20 into 10 to the power 3 is equal to n divided by pi by 2, 0.3 square. So you will get this n will be equal to 20 into 10 to the power 3 multiplied by pi by 2 into 0.3 square, and you will get this n will be equal to 2.827 kip. Put n is equal to 2.827 kip in equation number 1. And what is equation number 1? P is 1.547 times n. So P is equal to 1.547 multiplied by n. So 1.547 multiplied by 2.827 kips. You will get P is equal to 3.26 kip. And this P is based on, it is based on normal stress. Clear? So here you can see we have two values, one P is this one and another one is this one. So this largest load, I will write it over here, the largest tensile load, largest P which can be applied on this system is 3.26 kips, and which is the answer of our this question. Why we have selected this smaller one and called it as the largest load? Because you can see this load is less than this, so it will be safer. And if you put this P in this formula, if you put this P in this formula and then shear force in this formula. So it will exceed the allowable. Your shearing stress will be greater than this allowable shearing stress. So therefore, for safer design, we use P is equal to 3.26 kips. And that was all about this problem 1-77. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos in your community so that my channel may grow further and most of the students may learn from my videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 1-88 that is taken from chapter number 1, Stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the compound wooden beam is connected together by bolt at B, assuming that connection A, B, C, and D exert only vertical forces on the beam. Determine the required diameter of bolt at B and the required outer diameter of its washer. If allowable tensile stress for the bolt is 150 megapascal and allowable bearing stress for the wood is 28 megapascal. Assume the hole in the washer has the same diameter as the bolt. So you can see these are compound beams that are connected together by a bolt at B, and this reaction at A, B, C, and D only exert vertical force. All other loadings are shown over here. Clear? So you have to determine the diameter of this bolt. Clear? Diameter of this bolt and the washer that is used, the outer diameter of the washer that is used in this bolt. So let's start with the solution. So as this is a compound beam, so what we will do is that we will first draw the free body diagram FBD of member or beam CD. So you can see this is beam CD. So there is a vertical reaction force of D at D, which will be FD. There is this load, this load. Now the bolt will exert a load that will acting downward on this, and this reaction force by the C will be upward. So we will draw its free body diagram. So let me draw it first. Let this is the beam. Here you have to draw it. This is point C. So we have FC that will acting upward. This is C point. This is your D point. Clear? So your force D will be also upward. FD. There is a 1.5 2 kilonewton load acting at a distance of 1.5 meter from this. So this distance is 1.5 meter. There is another load which is also 1.5 kilonewton and acting at a distance of 1.5 meter from the 2 kilonewton load. Now this is point B. Clear? So the load that is acted upon by this, the bolt acts on this member or beam CD is FB. The distance between FC and FB is also 1.5 meter, and from B till then this load is also 1.5 meter. Now we'll apply equation of equilibrium in order to find this FB and FC. So what actually we are interested to find out this load FB. So what we are going to do is that we will apply equation of equilibrium that sum of all moment about point D is equal to 0 and taking the counterclockwise moment as positive. So first moment about point D will be equal to this force FB, and perpendicular distance is this sum of all this is 4.5 meter, and this is producing counterclockwise moment, so it will be positive. So I will write FB into 4.5. The second moment that is produced due to this 1.5 kilonewton load and the perpendicular distance is 3 clear meter, and this is also producing counterclockwise moment, so it will be positive. So I will write plus 1.5 into 3. The third load which is producing moment is this 2 kilonewton and perpendicular distance is 1.5 about point D, and it is producing counterclockwise moment, so it will be positive. So plus 2 into 1.5, and the last force which is producing moment about point D is FC, and this whole perpendicular distance is 6. This distance is 6 meter, and this is producing clockwise movement, so it will be negative. It will be negative. So I will write minus FC multiplied by 6 is equal to 0. So from here this will be equal to 4.5 times FB minus 6 times FC, and these two terms, this and this term, will give you minus plus 7.5. When move toward right side, it will be minus 7.5. That this is your equation number 1. Now what we will do is we will take the free body diagram of this beam AB. So you can see there is a vertical reaction force. The C will now act downward on this, and FB will be also upward on this, and there is a load. So we will draw this free body diagram. So I will write free FBD of member AB. So let me draw the free body diagram again. So you can see this is point A. So you will be having a reaction, vertical reaction force, which is FA. There is a 2 kilonewton load, 3 kilonewton load. You can see this is 3 kilonewton load that is acting at a distance of 2 meter from this side. Let this is point C. Clear? So at C you will be having a force that will be acting downward. Why? Because you can see that this force at C will be upward. So as there is Newton third law, it will be acting downward. So this is FC. Clear? And same FB here is downward. Clear? So here it will be upward. So let this point is your point B. So here it will be upward, FB. Clear? And all the distance between these two forces are 2 meter. Clear? And from C to B it is 1.5 meter. Now we will apply equation of equilibrium. So the equation of equilibrium which we will apply is sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, one moment that is produced due to this FB and perpendicular distance is 2 plus 2 plus 1.5 is 5.5, and this is producing counterclockwise moment, so it will be positive. So I will write FB into 5.5. Clear? The second moment that is produced due to this FC and perpendicular distance is 4. This is 2 and this is 2. So it will be 4 meter and it is producing clockwise moment, so it will be negative. So I will write minus FC multiplied by 4. The third moment will be produced due to 3 kilonewton load and perpendicular distance is 2, and this is producing clockwise, so it will be also negative. So I will write minus 3 into 2. And the sum of all moment about point A must be equal to 0. So what we will get is 5.5 times FB minus 4 FC is equal to 6. So from here you will get 4 FC is equal to 5.5 times FB minus 6. And if you divide 4 on both sides, so you will get 5.5 divided by 4 FB minus 6 divided by 4. And that will give you 5.5 divided by 4 will give you 1.375 times FB, and 6 divided by 4 is 1.5. And this is your equation number 2. Now what we will do is that put equation 2 in equation number 1, which is this one. You can see, so 4.5 times FB minus 6 times FC is 1.375, FB minus 1.5 is equal to minus 7.5. So 4.5 FB minus 6 multiplied by 1.375 is 8.25 times FB plus 6 multiplied by 1.5 is 9 is equal to minus 7.5. Clear? So minus 4.5 minus 8.25 FB is minus 3.75 FB is equal to minus 7.5 minus 9, which is equal to minus 16.5. And if you divide minus 3.75 on both sides, so you will get FB is equal to 4.4 kilonewton. So this is the force in the bolt. Now what we will do is that put FB in equation number 2. So you will get FC will be equal to 1.375 times FB is 4.4 minus 1.5, and you will get FC will be equal to 4.55 kilonewton. Okay, since we are in need of force in this bolt, so now we will calculate the diameter of this bolt. So what actually I will write is, we have been given allowable stress for this bolt is given as, which is equal to FB divided by area of bolt. So FB is 4.4 kilonewtons, so 4.4 into 10 to the power 3. Area of bolt is pi by 4. Diameter of bolt square. Clear? So allowable stress for the bolt is 28 megapascal. So I can write it 28 into 10 to the power 6 is equal to 4.4 multiplied by 10 to the power 3 divided by pi by 4 dB square. So from here you will get dB square is equal to 4.4 multiplied by 10 to the power 3 divided by pi by 4 into 28 10 to the power 6. And if you take square root on both sides, so you will get the diameter of bolt will be equal to it will be 0.00611 meter. Our diameter of bolt will be equal to 6.11 millimeter. So this is the answer of our first part. Now we'll move towards second part, and in second part we have been asked to find the outer diameter of washer. So for washer, so you can see if this is a circular washer, clear, the inside diameter will be diameter of bolt. So this will be dB, and we will need diameter of washer, outer diameter. Clear? This is dW. So bearing stress, you can see that this washer is in contact with this wooden piece, so bearing pressure will be there. So this allowable bearing stress for this wooden will be equal to FB divided by area of washer. Clear? So FB is 4.4 kilonewtons, so 4.4 into 10 to the power 3, and area of washer is pi by 4 dW square minus dB square. So diameter of bolt in meter is 0.00611. So 0.00611 square. And allowable stress for the wood is 28 megapascal. Okay, so 28 megapascal. So 28 into 10 to the power 6 is equal to 4.4 into 10 to the power 3 divided by pi by 4 into dW square minus 0.00611 square. So when you calculate it, dW, you can now find it, dW square will be, or dW, when you calculate it, it will be equal to 0.0154 meter, or that will be 15.4 millimeter. Also make a correction that here allowable tensile stress for the bolt is 150 megapascal. So I will write it as 150 megapascal. Correct it, 150 megapascal. So 150, here this will be also 150, and you will get this diameter of bolt. So make this correction, and that was all about this problem 1-88. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-90. This problem is taken from chapter number 1, stress, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum allowable load P that can be safely supported by frame if T is 1.25 inch, B is 3.5 inch. The wood has a normal failure stress of 6 ksi and a shear failure stress of 1.5 ksi. Use a factor of safety against failure of 2. So you can see this is the frame, clear, that is acted upon by load P. The thickness T is given as 1.25 inch and this B is given as 3.5 inch. And the normal stress, failure stress is 6 ksi and shear fairing stress is 1.5 ksi. So you have to find this P load for the factor of safety of 2. So let's start with the solution. So first step is that we will find internal loading. So internal loading. So for finding this force in member AB, we will use equilibrium of joint A. Joint A. So you can see here at joint A we have one load P. This member will exert a load in this direction, and similarly this FAC will exert force over in this direction. So we will draw the free body diagram over here so that this is your point P. So here you have 4 vertical force of P, which we will find here. This member AB will exert a force in this direction. Here this is FAB, and this is the member AC, which will exert force FAC in this direction, and this is your point A or joint A. Now you can see here that this is 30 angle. So if I draw a horizontal line from here, so using alternate angle, this angle will be also 30 degree and this will be also 30 degree. So this is 30 degree and this will be also 30 degree, because you can see this is 30 degree and this is also 30 degree. Now we'll find this FAB and FAC by using equation of equilibrium. So first equation of equilibrium is that sum of all force along x direction must be equal to 0 and force in this direction is taken as positive. So this force will have two components. One along x-axis, this component will be equal to FAB cos of 30 degree, and similarly this will have one horizontal component in this direction. This will be equal to FAC cos of 30 degree, and this component will have one vertical component which is FAB sine of 30 degree, and this will have vertical component FAC sine of 30 degree. So by using this equation of equilibrium, so FAB cos of 30 degree, which is horizontal component in positive direction, minus FAC, which is horizontal component of FAC, and in opposite direction their sum must be equal to 0. So from here FAB will be equal to FAC cos of 30 degree divided by cos of 30 degree. So that will be equal to FAC. So FAB is equal to FAC. So we have one equation is this one. Now we'll apply another equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So minus P plus FAB sine of 30 plus FAC sine of 30 will be equal to 0. So I will write minus P plus FAB sine of 30 degree plus FAC sine of 30 degree is equal to 0. Now you can see FAB is equal to FAC, so I will replace this FAC with FAB. So FAB sine of 30 degree plus this FAB sine of 30 degree plus this minus P. So 2 times FAB sine of 30 degree is equal to P. And when you calculate this FAB, so FAB will be equal to P divided by 2 sine of 30 degree, and that will be also equal to P. Clear? So it means that this FAB is equal to FAC is equal to P. Okay. Now what we will do is that you can see that this FAB is acting on this member at this point B will be in this direction as per Newton's third law. So you can see here this is support. So we will find this reaction force FBX and this FBY. So basically the horizontal component of force acting on joint B can be determined. We are interested in this because this is producing shear in this area. So that can be found by using a free body diagram of joint B. So I will write it using joint B. So this is joint B where you have this FAB acting that is making 30 degree there. So at point B you will be having horizontal force, reaction force FBX, and there will be a vertical reaction force which is FBY. So we are interested to find out this horizontal component. So this component can be obtained by using equation of equilibrium that sum of all forces in an x direction must be equal to 0 and force in this direction is taken as positive. So FBX component minus this force will have two component. One is y direction and other one is in x direction. So this component will be FAB cos of 30 degree. So I will write minus FAB cos of 30 degree is equal to 0. So FBX component will be equal to FAB cos of 30 degree. Since FAB is equal to P, so it will be equal to P into cos of 30. So this is FBX. Clear? Now you can see that this FAB is acting on this member is like this at this joint. Clear? So if we take out this section, this portion as AA, this line, let me draw it from this point. This is section AA. So this FBX is acting over here, which is causing shear force or shearing of this. Clear? So as a result, shear force VAA will be equal to this FBX. So let me draw the free body diagram of this B, of this portion. So let this is the wooden piece having breadth B. Clear? And the net force acting on it is FBX, which is equal to P cos of 30 degree. Clear? And this P cos of 30 degree will be equal to 0.8660 times P. 0.866 times P. So as a result, there will be a shear, horizontal reaction shear force. So by using equation of equilibrium, we will find this and you will get VAA minus 0.866 P is equal to 0. So VAA is equal to 0.866 P. Now you have shear force and you have normal force in portion FAB. So we will use, we will find allowable, normal stress and shear stress. So how you will find normal stress? So we know that factor of safety is equal to failure stress divided by allowable stress. Here, so from here, allowable normal stress is equal to failure stress divided by factor of safety. So failure stress is given as 6 ksi and factor of safety 2. So 6 divided by 2 is equal to 3 ksi. Now similarly, factor of safety is equal to failure shear stress in failure divided by allowable shear stress. So from here, allowable shearing stress is equal to shearing stress in failure divided by factor of safety. So that is 1.5 divided by 2. Let me check it. This is 1.5 divided by 2 is equal to 0.75 ksi. Now using this formula, we know that allowable normal stress is in member AB is FAB divided by area of AB. So allowable stress is 3 ksi, so 3 into 10 to the power 3. FAB is P. You can see FAB is equal to P divided by area of AB. So you can see this thickness is T, which is 1.25, and this breadth is also 3. So 3, this is 1.25, and this is 3.5 inch. So this is the cross-sectional area. So I will write 1.25 multiplied by 3. So P from here you will get P will be equal to 11.11250 pounds, or P will be equal to 11.25 kg. But that is for allowable normal stress. Now we'll use allowable shearing stress, and we know that allowable shearing stress is equal to horizontal shear force divided by shearing area AA. So from here, allowable shearing stress is 0.75 ksi, 0.75 into 10 to the power 3 is VAA. So VAA is 0.866 times P divided by shearing area. So you can see this is the shearing area. This is the width and length B, and this is the thickness 3. So 3B. B is also given as 3.5. Clear? So I will write it 3 multiplied by 3.5. So from here you will get P will be equal to 9093.27, that is 9.09 kg. So now you have two loads. One P is this one, another one is this one. So we will choose the smallest value for the safer design. So your P is equal to 9.09 kg. That can be applied to this system. And that was all about this problem 1-90. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 3-23 that is taken from chapter number 3, Mechanical Properties of Materials. That is taken from Mechanics of Material by R.C. Hibbeler. So statement is the stress strain diagram for many metal alloys can be described analytically using Ramberg-Osgood 3-parameter equation, which is this one, where E, K, and N are determined from measurement taken from this diagram. Clear? Using the stress strain diagram shown in the figure, take E is 30 into 10 to the power 3 KSI, determine the other two parameter K and N, and thereby obtain an analytical expression for the curve. So you can see this is stress strain curve and this is Ramberg-Osgood equation. So you have to find this K and N. Clear? So let's start with the solution. So as per Ramberg-Osgood equation, we have strain is equal to stress divided by modulus of elasticity plus K into stress power N. This is your equation number 1. Clear? Now from stress strain diagram, we will calculate this. We will calculate the stress and strain. So for, you can see here, this is stress, which is 40. So as per this stress, we have strain 0.1. So if stress is 40 KSI, clear, and your strain is 0.1. Put these values in equation number 1. So what you will get is that strain is 0.1, stress is 40 KSI. So 40 divided by E is 30 into 10 to the power 3 KSI plus K, which is not known, is sigma is 40 power N. So from here you will get 0.1 is equal to 0.00133 plus K into 40 power N. And if you further simplify it, so 0.1 minus 0.00133 is equal to K into 40 power N. And this will give you 0.09867 is equal to K into 40 power N. This is your equation number 2. Now again, from stress strain diagram, we will choose another value of stress and strain. So you can see, you can choose this point. You can choose any other one, but these are feasible. So stress is 60 and strain is 0.3. So I will write it, strength is equal to 60 KSI and strain is 0.3. So put it in equation 1 again. So when you put it, you will get 0.3 is equal to 60 divided by E is 30 into 10 to the power 3 plus K into 60 power N. And if you further simplify it, 0.3 is equal to 0.002 plus K into 60 power N. And we will get 0.3 minus 0.002 is equal to K into 60 power N. And this term will give you 0.298 will be equal to K into 60 power N. This is your equation number 3. Now what we will do is that we will divide equation 2 by equation 3. So this is equation number 2, 0.09867 is equal to K into 40 power N. And we will divide it by equation 2, which is 0.298 divided by K into 60 power N. And you will get 0.3311 kk will cancel each other here, and we will left with 40 power N divided by 60 power N. And that will give you 40 divided by 60 power N will be equal to 0.3311. And from here you will get 0.3311 will be equal to 0.6667 power N. Now what we will do is that take natural logarithm on both sides. So what we will get is ln of 0.3311 will be equal to ln of 0.667 power N. So from here you will get ln of 0.3311 will be equal to N times ln of 0.6667. And we are interested to find N. So N will be equal to ln of 0.3311 divided by ln of 0.6667. So N will be equal to, this will give you minus 1.105 divided by minus 0.404. So you will get N will be equal to 2.73. So this is the equation. N is equal to 2.73. Now what we will do is that put N is equal to 2.73 in any equation, either equation 2 or 3. So here I am going to put it in equation 2. So equation 2 is this one. So you will get 0.09867 is equal to K into 40 power 2.73. Okay, and K will be equal to 0.09867 divided by 40 power 2.73. And when you solve it, you will get K will be equal to 4.17 into 10 raised to the power minus 6. Clear? So these are the value of N and K. And if you put it in this equation, so your final Rambert-Osgood equation will become equal to strain is equal to stress over E plus K was 4.17 into 10 raised to the power minus 6 into sigma power 2.73, which will be your final equation that is being asked to obtain an analytical expression for the curve. And this equation is valid only for this curve. And that was all about this problem 3-23. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 14-3. This problem is taken from chapter number 14, that is energy methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the strain energy in the step rod assembly portion. A, B is steel and BC is brass. Modulus of elasticity of brass is 101 gigapascal while steel is 200 gigapascal. Yield stress of brass is 410 megapascal and yield stress of steel is 250 megapascal. So you can see this is the step rod that is acted upon by axial loading at point C and B, and this is fixed at point A. The diameter is given for rod AB is 100 millimeter while BC is 75 millimeter. So we have been asked to find the strain energy in this step rod. Clear? So let's start with the solution. So first we will define what is strain energy. So again, you can see when you applied load on the body, clear, that will tend to deform this body. Provided no energy is lost in the material, the external work done by the load will be converted into the internal work, which is called strain energy. So basically the external workload is work done on the body will be stored in the body as strain energy. This is what we call strain energy. Now you can see that this is axial loads, all are axial loads, and we know that, and this is step rods, this is one rod and this is second rod. So we can write strain energy, which is represented as UI for axial loading. Since this is axial loading, it is equal to sum of N square into L divided by 2 times AE. Clear? Where N is normal or axial force, L is length, A is area of that rod, and E is modulus of elasticity. Now what we will do is that first step is that if we cut this step rod over here at section 1-1, let this is section 1-1. So at section 1-1, if I cut it and draw the free body diagram, so it will be like this. This is your point C, where you have 20 kilonewton load, and in order to keep it in equilibrium, you will be having reaction force opposite to that. Let this is NBC because this is rod BC. Now you can find this NBC by using equation of equilibrium, that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So NBC is positive minus 20 kilonewton is equal to 0. So from here you will get NBC will be equal to 20 kilonewton. Okay, now what we will do is that we will take another section, which is section 2-2 in rod AB, and we will draw the free body diagram that is available on the right. So at section 2-2, draw the free body diagram. So this way there is a larger rod there and there is a smaller rod, which is rod BC. There. So at this point you have 20 kilonewton there, which is your point C. There. This is your point B, where you have 30 kilonewton, and here you will have also 30 kilonewton. So when you cut it, you will be having a reaction force. Now you can see 30 plus 30 is 60 in this direction, plus 20, which is 80. So in order to keep it in balance, this reaction force should be in this direction, and this will be NAB because this is in rod AB. So you can find this NAB by using this equation of equilibrium and taking this direction force positive. So NAB minus 30 minus 30 minus 20 is equal to 0. So NAB will be equal to 80 kilonewton. Now you have both normal or axial forces in this rod AB and BC. So what we will do is that we will use this equation. So strain energy due to axial loading is equal to sum of, so for rod AB, it will be equal to NAB into length, NAB square into length AB divided by 2 times of area of AB into E. AB is made up of steel. You can see where this is made up of steel. So E of steel plus for brass or for rod BC, NBC square into length of BC divided by 2 times of area of BC, and this BC is made up of brass. Clear? It is given ahead, this is made up of brass. So now you have all the values, so you can put it. So NA is, again NAB is 80 kilonewton. So 80 and kilo is 10 raised to power 3 whole square. Length of AB is 1.5 meter. So I will write 1.5 divided by 2 multiplied by area. So you can see diameter is given 100 millimeter, which is 0.1 meter. So you can use pi by 4 into 0.1 square. Clear? And E of steel is also given as, you can see this is 200 gigapascal. So 200 into 10 raised to power 9. Similarly, you can do it for N for rod BC. So NBC is 20 kilonewtons. So 20 into 10 raised to power 3 whole square. Length of BC is 0.5 divided by area, 2 times area of BC. So diameter is given as 75 millimeter, which is equal to 0.075 meter. So pi by 4 d square. So pi by 4 0.075 square into E of brass. So E of brass is 101 gigapascal. So 10 raised to power 9. This will give you strain energy due to axial loading. So when you calculate it, you will get strain energy due to axial loading comes out to be 3.28 joules. So this amount of energy is stored in the body due to external work. But we will check it again. So this result is valid. This result will be valid only when your stress is less than the yield stress. So what we are going to do is this. First we will find stress in AB, which is equal to NAB divided by area of AB. So NAB is 80 kilonewtons, so 80 into 10 raised to power 3, and area is pi by 4, 0.1 square. Clear? And when you calculate it, you will get 10.19 into 10 raised to power 6 Pascal, or you can see 10.19 megapascal. Now you can see that stress in AB is less than yield stress of this steel. Clear? You can see AB is made up of steel, which is this one, 250 megapascal. So this 10.19 is less than megapascal, is less than 250 megapascal. So it means that this is okay. We will check it for BC. So sigma BC is equal to NBC divided by area of BC. So NBC was 20 kilonewton. So 20 into 10 to the power 3 divided by area. So pi by 4, 0.075 square. Okay. So again, when you calculate it, you will get stress in normal stress in BC, and that come out to be 4.527 into 10 to the power 6 Pascal, or you can say 4.527 megapascal. And you can compare it sigma BC and sigma yield of brass. So you can see this is BC 4.257, while yield stress of brass is 410 megapascal. So you can see this is 4.527 megapascal is less than 410 megapascal. So it means that your strain energy is stored in this body is 3.28 joules. And that was all about this problem 14-3. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel, as well as they will learn from my videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 14-5, and that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is using bolts of the same material and cross-sectional area, two possible attachment for cylinder heads are shown. Compare the strain energy developed in each case, and then explain which design is better for resisting an axial shock or impact load. So you can see this is design A and this is design B, and this is a piston, clear, and this is the cylinder head. So this is one arrangement using 4 bolts of each length L1, and here you can see the cylinder head is held by this single bolt of L2 on each sides. Clear? So you have to find the strain energy in this case and in this case, and then we will compare which one is better. So let's start with the solution. So for case A, you can see due to this movement of this piston, there will be shock or axial load in this bolt, and again the bolt experience tensile stress or axial stress. So we know that strain energy due to axial load can be represented as UIA. Since this is for case A, so I will write A, and that is equal to N square L1 divided by 2AE. Since area and material, cross-sectional area and material is same, so I will write AE. N is the normal stress or normal force in this bolt, where L1 is the length of this bolt, which is L1. So this is the strain energy in case A. Now for case B, you can write the same equation. UI for case B will be equal to, here you can see this bolt will experience normal load or axial load. NA, the bolt will be in tension, so it will be equal to N square, and length over here is L2 for case 2. A 2 times A into E. So this is the strain energy for the case B. These are the answer of our first part. Now in second part, we have to explain which design is better. So explanation is that I will write it. So you can see ui for B is greater than ui for A case. Why? Because here length is increased. All other factors are same, but length is increased in case B. Therefore, ui for B is greater than ui A, strain energy in case A. The reason I will also write L2 is greater than L1. So the design case B is better able to absorb energy. So our answer is case B is better choice. And this was all about this problem 14-5. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon. So welcome back. In this video, we are going to solve problem 14-10 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the shaft assembly is fixed at C. The hollow segment BC has inner radius 20 mm and outer radius of 40 mm, while solid segment AB has a radius of 20 mm. Determine the torsional strain energy stored in the shaft. The shaft is made up of 2040 T6 aluminum alloy. The coupling at B is rigid. So you can see this is shaft BC and this is shaft AB. The end C is fixed. There is a coupling between B, A, and in shaft BC and AB, which is rigid. At point A, we have a clockwise torque of 30 Newton into meter. At coupling, we have 60 Newton into meter, clockwise torque of 60 Newton into meter. And this BC is hollow. Inner radius is given as 20 millimeter CI and C outer for BC is 40 millimeter, while solid segment AB has radius 20 millimeter. So you have to determine the torsional strain energy stored in this shaft. So let's start with the solution. As we know that strain energy due to this torsion is equal to sum of T square into L divided by AB. Why this formula? Because you can see we have two different sections, so here we will find this torque. So for this portion AB, this formula will become equal to UI due to torsional will be equal to TAB square into LAB divided by GJ. This is not AB, this is GJ. So GJ. So JAB. Material is same, only diameters are different. And this for segment BC, it will be TBC square into LBC divided by GJBC. Now, how we'll find torque AB? So we will cut this in segment AB. So I will write for segment AB. When you draw it, the free body diagram will be like this. Clear? Here you have, this is the axis, for example, x-axis. So at this is your point A. So here at A, you have a clockwise torque of 30 Newton into meter. So in order to balance it, you have TAB is you will be having TAB. In order to find TAB, we will apply equation. Sum of all moment about x-axis must be equal to 0 and counterclockwise taken as positive. So torque TAB, which is counterclockwise, and the other one which is minus 30, their sum must be equal to 0. So it means that TAB is equal to 30 Newton into meter. So this is the torque in internal torque in this segment AB. Now we will apply for, we will find for the segment BC. For segment BC, I will cut it along any length of BC and draw the free body diagram. So it will be like this. This is BC. Clear? There is a coupling over here, and then we have another segment which is segment AB. Okay. At this point, this is point A, where you can see you have clockwise torque of 30 Newton into meter. This is coupling here at our point B. So at point B, we have a torque of 60 Newton into meter clockwise. So this is the axis. Clear? So the net torque will be equal to counterclockwise, and that will be TBC. So how you'll find this TBC? By using this equation of equilibrium. Now we'll apply TBC is counterclockwise, so it will be positive. Minus 60 minus 30 will be equal to 0. So from here, TBC will be equal to 90 Newton into meter. Now you have TAB and TBC. Length of AB is given as 600 millimeter, which is equal to 0.6 meter. Here, 0.6 meter. Length of BC is also again 600 millimeter. That will be equal to 0.6 meter. G, we will find G by using mechanical property table. So for T, 2014 T6 aluminum alloy, we will find G. So G for this will be equal to, again, you will go to the property table. Again, we have to find this table. You can see this is the table. And here from this, T 2014 T6. So G is 27 gigapascal. Clear? So note down it 27 gigapascal. So G is 27 gigapascal, or that is equal to 27 into 10 to the power 9 Pascal. Now what about JAB and JBC? So JAB is for solid segment. For solid segment, JAB is equal to pi by 2 CAB power 4. CAB is given as 20 millimeter. So in meter, it will be equal to pi by 2, 0.02 power 4. and that will give you 80 into 10 to the power minus 9 pi, and unit will be meter power 4. Okay, now for hollow segment BC, hollow segment BC, this JBC will be equal to pi by 2 C outer of AB, BC, not AB, BC power 4 minus C inner of BC power 4. Okay, so you can put the value pi by 2. C outer was 40 millimeter. Clear? Let me check it. That is, C outer is 40 and C inner is 20. Okay, so 40 is 0.04 meter. Clear? Power 4 minus C inner, it was 20, and that 20 millimeter, which is 0.02 meter, power 4. That will be polar moment of inertia for this hollow segment BC. Again, when you solve this, you will get 1200 into 10 to the power minus 9 pi, and unit will be meter power 4. That will be JBC. When you have all these values, you can just put it in this formula, clear, which was strain energy due to torsion will be equal to TAB square into LAB divided by G JAB plus T square BC LBC divided by G JBC. So put the value TAB is 30 Newton meter. So 30 square into length is 0.6 divided by G is 27 gigapascal, and J is 80 into 10 to the power minus 9 times pi, plus TBC. TBC, you can see 90. So 90 square multiplied by length is 0.6 divided by G is 27 into 10 to the power 9, and J is 1200 into 10 to the power minus 9 times pi. That will give you strain energy due to torsion. And when you solve this, you will get 0.06379 joules. Or strain energy due to torsion will be equal to 0.0638 joule. So this is the amount of strain energy that will be stored in the shaft due to the applied torque. And that was all about this problem 14-10. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-20 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the concrete column consists 6 1-inch diameter steel reinforcing rod. If the column supports a load of 300 kips, determine the strain energy in the column. E of steel is 29 into 10 to the power 3 ksi, while E of concrete is 3.6 into 10 to the power 3 ksi. So you can see this is the concrete column that consists of 6 this 1-inch steel rod, and the load that it supports is 300 kips. So you have to find the strain energy in this column. So let's start with the solution. So first step is that if you cut this column and draw the free body diagram. So let me draw it first. That this is the frontal view of this column. There is a load of 300 axial load which is acting 300 kips here, and you can see that this load is acting on this concrete column. So some of load is taken by concrete and some of the load is taken by this steel reinforcing rod. So I will write as a result this load will be equal to P of concrete, and some of the load is taken by P of steel. So we will apply equilibrium condition in order to write the equation. So this is the equation that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see minus 300, which is downward, plus P of concrete plus P of steel is equal to 0. So from here we can say that P of concrete plus P of steel is equal to 300. Means that this 300 kips load is taken, some of portion is taken by concrete while some is taken by this steel rod. So this is your equation number 1. Now you can see that due to this load there will be deformation in this concrete as well as in this steel rod. Since both are same, both are joined with each other, so their deflection will be same. So we will write compatibility equation. So compatibility equation, which is equal to change in length of concrete is equal to change in length of steel. Okay, as we know that change in length is equal to P into L divided by AE, that this change in length is due to axial load. Clear? So for concrete I will write P of concrete into length, both lengths are same, divided by, I will write it, length of concrete is equal to length of steel, and that is equal to L, divided by area of concrete into E of concrete, that will be equal to P of steel into L of steel, which is equal to L divided by area of steel into modulus of elasticity of steel. So you can see this L will cancel with each other, so we will left with P of concrete divided by area of concrete into EC is equal to PS divided by AS into ES. Now we will calculate this area of concrete. So area of concrete, you can see this is the area. The diameter is given, the radius is given as 12 inch. So radius of concrete is given as 12 inch here. So there are six 1 inch diameter steel rods. So this area of concrete will be equal to this minus the area of this six steel rods. So I will write area of concrete is pi r square, rc square, minus 6 times the area of steel rod. So area of steel rod is 6 multiplied by pi r s square. Clear? Now what is this? So pi area of radius of concrete is given as 12. So pi 12 square minus 6 times pi. What is diameter of steel rod is given as 1 inch. So radius will be 0.5. So 0.5 square. So this is the area of concrete. Now area of steel is equal to pi r square, pi rs square. So that is equal to pi multiplied by 0.5 square. Since there are 6 rods, so I will multiply by 6 multiplied by on both sides. Clear? So now you can put the value P of concrete divided by area of concrete is pi into 12 square minus 6 times pi into 0.5 square. Multiply by E of steel, E of concrete, which is 3.6 into 10 to the power 3. So 3.6 into 10 to the power 3. That will be equal to P of steel divided by area of steel is 6 into pi into 0.5 square. And what about E of steel is also given as 29 into 10 to the power 3 KSI. So I will write 29 into 10 to the power 3 KSI. Okay, so when you solve this, P of concrete will be equal to 11.7931 P of steel. Yeah, that this is your equation number 2. Now put the value of P of concrete in equation number 1. So put equation 2 in equation 1. So P of concrete is 11.7931 PS plus PS is equal to 300. What I did is that I replaced P of concrete with its value and P of steel was there. So their sum must be equal to 300. Okay. Now when you solve this, it will be from here you will get P of steel will be equal to 23.45 kip. So out of 300 kip steels, each steel rod takes 23.45 kips load. This is equation number 3. Now put equation 3 in equation 2. So P of concrete is equal to 11.7931 into P of steel, so which is 23.45 kip. And you will get P of concrete will be equal to 276.55 kip. Okay, so it means that concrete is taking 276.55 kip load, while the six steel rods are taking 23.45 kips load. Now you have all the loads, so we will find the strain energy due to axial loading, that is equal to sum of N square L divided by 2 AER. We have written here P, so it will be equal to sum of P square L divided by 2 AE. So just put the values. So I will write it for P of concrete square into length divided by area of concrete into EC plus P square of steel into L divided by 2 times E of area of steel. So there are 6 steel, so I will write 6 multiplied by AS into E of steel. Now put the value, so you will get U strain energy due to axial loading will be equal to P of concrete is 276.55 square multiplied by length. We will check the length. Length is 5 feet. So in inch it will be 60 inch. 12 into 5. We'll convert it into inch. 2 multiplied by area of concrete, which is again this one. Clear? So I will write it pi into 12 square minus 6 multiplied by pi into 0.5 square into E of C, which is 3.6 into 10 to the power 3 plus P of steel, which was 23.45 into length is 5 feet. So 5 into 12 will give you in inch divided by 2, and area of steel 6 steel rod is this one. So 6 multiplied by pi into 0.5 square multiplied by E of steel, which was 29 into 10 to the power 3 KSI. So when you solve this, you will get strain energy due to this axial loading will come out to be 1.544 kips into inch. And if you want to convert it into feet, you have to divide it by 12. So you will get 0.129 kip into feet. And which is the answer of our this question. And that was all about this problem 14-20. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for watching. Welcome back to another episode that is about problem number 14-22. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement of this problem is determine the bending strain energy in the beam and the axial strain energy in each of two posts. All the members are made up of aluminum having a square cross section 50 millimeter by 50 millimeter. Assume the post only support vertical axial load. Modulus of elasticity of aluminum is 70 megapascal. So you can see this is the beam and the loading is shown. There is a distributed load of 8 kilonewton per meter, and there are two vertical posts that support this beam. So you have to find the bending strain energy in this beam and axial strain energy in this vertical post. So this vertical post offer only vertical reaction. So let's start with the solution. So what if we remove this post, two posts? So this will apply a vertical reaction on this beam. Let this is the beam. You can see this is the load that due to this post. So this is P of that this the load that this post apply on the beam is P of post, and similarly on other side the same length or same material post is applying a load P of post on this beam. There is a uniformly distributed load on this beam which is given as 8 kilonewton per meter here, and this load is downward. So we will find this P of post by using equation of equilibrium. So what will be the equation of equilibrium? So first step is that we will convert this distributed load into a point load. So this will be equal to 8 kilonewton per meter multiplied by the length, and the total length of this beam is given as 3 meter. I will multiply it with 3, so this 3 meter. So this will give you 24 kilonewton load, and that will act at a distance of 3 divided by 2, which is 1.5 meter from either side. Clear? Okay, now we will apply equation of equilibrium. So you can see the sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So P of post plus P of post. P of post is the load that this post apply on this beam. Minus 24 is equal to 0. So 2 times P of post is equal to 24. So it means that P of each post apply a 12 kilonewton load on this beam. Clear? Now we will move further, and what we will do is that we will cut this beam at any length x. Clear? And we will draw the free body diagram in order to find the equation for movement. So look, you can see this is the beam. Here we have one load P of post, which is equal to 12 into 10 to the power 3 Newton there, and this total length of the beam where we cut it is x, and there is a uniformly distributed load on this which is 8 kilonewton per meter. So when you cut it, you will be having a shear force and you will be having a moment. This is your point 1. So what we will do is that we will convert first this distributed load into a point load. So this will be equal to 8 multiplied by 8 kilonewton. So 8 into 10 to the power 3 multiplied by this length x for which it acts. And this will act at a distance of x by 2 from either side. So this distance will be x by 2. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about point 1, one moment is this reaction moment which is counterclockwise, and that will be plus. The second moment will be due to this 8 into 10 to the power 3 into x, and the perpendicular distance is x by 2, and this is also counterclockwise, so it will be positive. So plus 8 into 10 to the power 3x multiplied by x by 2. And the last moment that is produced due to this load and perpendicular distance is x, and this is producing clockwise, so it will be negative. So I will write minus 12 into 10 to the power 3x is equal to 0. So what I will get is m plus 4 into 10 to the power 3x square minus 12 into 10 to the power 3x is equal to 0. So if you further simplify it, this moment will be equal to 12 into 10 to the power 3x minus 4 into 10 to the power 3x square, and its unit will be Newton into meter. Okay, now this is the equation of movement. So we will move toward finding the bending strain energy due to bending, and we know that this is equal to integral from 0 to L m square dx divided by 2ei. Okay, so put the value integral 0 to L m square is 12 into 10 to the power 3x minus 4 into 10 to the power 3x square whole square into dx divided by 2ei. That is strain energy due to bending. Okay, now if you take this 1 over 2ei out of this integral, because these are constant, so you will left with 0 to L. So 12 into 10 to the power 3 square will be 144 into 10 to the power 6 x square minus plus 4 into 10 to the power 6 10 to the power 3 will be 16 into 10 to the power 6 x power 4 minus 2 times this term multiplied by this term will give you, I will directly write it, this will give you minus 96 into 10 to the power 6 x cube into dx. That will be equal to strain energy due to bending. Okay, again this bending strain energy will be equal to 1 over 2ei, and what we will take is integral. So 144 into 10 to the power 6 x cube over 3, and limit will be from 0 to L, plus 16 into 10 to the power 6 x5 divided by 5, and limit from 0 to L, minus 96 into 10 to the power 6 into x power 4 divided by 4, and limit from 0 to L. Okay, and you can see x start from 0 to x is equal to L, 3 meter, not L, 3. Total length is 3. So what is that? I will remove this L and I will write it 3. Okay, now we will find E of steel is given as 70 gigapascal, and it is given that this is square cross section 50 by 50. So the square cross section is this one. This is 50 millimeter, and the height is also 50 millimeter. Clear? So moment of inertia is equal to 1 over 12 BH cube. So 1 over 12, that is 50, and millimeter in meter it is 0.05, and height is also 50, which is 0.05 meter whole cube. So when you calculate it, you will get 0.52083 into 10 to the power minus 6 meter power 4. Now you have all the values, so you can just put it 1 over 2 multiplied by E is 70 gigapascal, 70 into 10 to the power 9 multiplied by 0.520 into 10 to the power minus 6 multiplied by all these values. 144 into 10 to the power 6 divided by 3x cube plus 16 into 10 to the power 6 x5 divided by 5. Limit will be from 0 to 3. Here limit from 0 to 3 plus minus 96 into 10 to the power 6 x4 divided by 4. Limit from 0 to 3. Okay. So when you solve this, you will get 1777 joules, or that is equal to 1.78 kilojoule. So this is the amount of bending, this is the amount of strain energy that will be stored in the beam due to bending. Now what we will do is that we will find the axial strain energy. Axial strain energy. Let me write it here. This is bending strain energy. Okay. For axial strain energy, we know that strain energy due to axial loading is equal to integral of 0 to L n square dx divided by 2 AE. Clear? So what we will do is that we have n is actually the normal load or axial load. So you can see the axial load of this post is PS 12 kilonewton. This beam is applied 12 kilonewton load on this post. So I will write from 0 to L 12 kilonewton, so 12, and that is also equal to, since it is equal to n square L divided by 2 AE. Okay, so 12 into 10 to the power 3 whole square. I will remove these things because this is already, we know that axial strain energy is equal to normal load square into L divided by 2 AE. So if you write this or this, both will give you the same thing. And length of each post is 1.5 meter. So 1.5 divided by 2 times area. Area of this cross section is given. So area is 0.05 multiplied by 0.05. And E is 70 gigapascal, 70 to 10 to the power 9. That is due to axial loading. So when you calculate it, you will get strain energy due to axial loading will comes out to be 0.617 joule. So this is the amount of strain energy that will be stored in each of the post. Clear? And that was all about this problem 14-22. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help them in learning, as well as help me in growing my channel further. Thank you for watching and thank you for your support. Welcome back. Problem 14-30. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the vertical displacement of NB of the cantilever 661 T6 aluminum alloy rectangular beam. Consider both shearing and bending strain energy. So you can see this is a cantilever beam having a point load 150 kilonewton at NB. The cross section of this cantilever beam is rectangular. Height is 300 millimeter while width is 100 millimeter. So you have to consider both shearing and bending strain energy, and then you have to find the displacement of this point B, which is delta B. So you can see due to this load, this beam will bend like this. So this will be the delta B, which we will have to find. So let's start with the solution. So we know that total strain energy, including shearing energy, will be UI due to shear plus strain energy due to bending. So we'll find this strain energy due to shearing as well as strain energy due to bending. For that, I have to cut this beam at a distance of X from this end B, clear, and we will draw the free body diagram. So let me draw the free body diagram. This is the beam. This is the distance X. This is point B, having a point load of 150 kilonewton. So when you cut this beam, you will be having a shear force and you will be having a moment M. And this is point O. So we'll first find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0, and taking the counterclockwise moment as positive. So about point O, one moment is due to 150 and perpendicular distance is X, and this is producing clockwise moment, so it will be negative. So I will write minus 150 into perpendicular distance X. The another moment is due to this external or reaction moment, which is counterclockwise and is taken as positive. And sum of all this moment about point O is equal to 0. So from here we will get moment is equal to 150 times X. Now what will about shear force? So we'll also find this shear force by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So V minus 150 that is in kilonewton into 10 to the power 3 is equal to 0. So from here we will get the shear force equal to 150 into 10 to the power 3 Newton. Okay, now you have both this value. So what we will do is that we will first find the shearing strain energy. So shearing strain energy. So we know that strain energy due to shear, vertical shear, is equal to integral of 0 to L Fs V square into dx divided by 2Ga. This is the formula. And what is Fs? So Fs is form factor. Fs is equal to form factor. And for rectangular shape, this Fs is equal to 6 by 5. And what is about G? So G is modulus of rigidity. We'll find it from property table, and A is the area. So you can see the height is 300 and width is 100. So 300 in meter is 0.300 and width is 0.1. So this will be the area. Okay. Now for G we'll go to the property table, and you can see here that this is the property table, and we have 6061 T6. 6061 T6, and G is 26 gigapascal. So we'll write the value 26 gigapascal. 26 into 10 to the power 9 Pascal. Okay, now we have all the value. V is there, all the values there, so you can just put it 0 to from L, and X start from 0 to X start from till 1. So 0 to 1, Fs is 6 over 5 V square. So V is 150 into 10 to the power 3 whole square into dx divided by 2 times G is 26 into 10 to the power 9, and area is 0.3 multiplied by 0.1. That will give you strain energy due to shear force. So when you calculate this, so you will get strain energy due to shearing comes out to be 17.31 joules. So this is the strain energy due to shearing. Now we'll find the strain energy due to bending. Strain energy due to bending. And we know that strain energy due to bending is equal to integral from 0 to L m square dx divided by 2EI. What is the value of E? So E can be taken from this table. Again, you can see E is 68.9 gigapascal. So I will write E is 68.9 into 10 to the power 9 Pascal. And what about I? I is the second moment of inertia for this rectangular section. It is equal to 1 over 12 breadth, which is 100 millimeter, and that in meter is 0.1, and height is 0.3, and it will be Q. So when you calculate, it will give you 0.225 into 10 to the power minus 3 meter power 4. Yeah. So you can just put it in this formula. Strain energy due to bending will be equal to integral from 0 to L. Moment is 150. You can see 150 into 10 to the power 3 x. Clear? Why 150? Because the unit will be kilonewton into meter. So in order to convert into Newton into meter, we will multiply 10 to the power x into whole square into dx divided by 2EI. E is 68.9 into 10 to the power 9, and I is 0.225 into 10 to the power minus 3. Okay. Now, if you further simplify it, and you will get, if you take all these constants, 150 into 10 to the power 3 whole square divided by 2 multiplied by 68.9 into 10 to the power 9 multiplied by 0.225 into 10 to the power minus 3 integral of 0 to L, and L will be 1, because you can see x start from 0 till x is equal to 1. We will left with x square dx. And again, when you solve this, you will get this value 725.689 integral of 0 to 1 x square into dx, and that will be 725.689. This will be x cube divided by 3 and limit from 0 to 1. So that will be 725.689 into 1 cube minus 0 cube divided by 3 will give you strain energy due to bending. And lastly, when you solve this, you will get the strain energy due to bending comes out to be 241.90 joules. Now this is the strain energy due to bending. So strain energy due to shear is this, and strain energy due to bending is this. So we know that total strain energy, which is Ui, is equal to Ui due to shear plus Ui due to bending. So add them both, 17.31 plus 241.90, and that will give you 259.20 joules. So this is the total strain energy. Now we will move above, and you can see due to this load 150, this beam will deflect like this. So its original axis. So this is the distance delta, that delta B will move, vertical displacement of delta B. So due to this external load, we have due to this external work will be done, and the work done will be stored in the form of strain energy, which will be equal to 1/2 this load 150 into 10 to the power 3 multiplied by this delta B. Clear? So I will write it, strain energy due to external load slash work will be equal to UE, and that will be equal to 1/2 150 kilonewton was the load into delta B. Okay, now we have both these equations. So by conservation of energy, this external work that is done on the object will be stored in the form of internal strain energy. So UE will be equal to UI. So UE is 1/2 into 10 to the power 1/2 into 150 into 10 to the power 3 multiplied by delta B will be equal to 259.20 joules, and delta B will be equal to 259.20 multiplied by 2 divided by 150 into 10 to the power 3. So when you solve this, you will get this vertical displacement of point B comes out to be 3.456 into 10 to the power minus 3 meter, or this delta B in meter, vertical displacement of point B will be equal to 3.46 millimeter, which is the answer of our this question. And that was all about this problem 14-30. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing further. Thank you for your support.